Megan DeMello.
I'm John Erickson, and we're going to talk about our heat exchanger optimization.
The purpose of this project was to create a heat exchanger that will transfer 1 megawatt through thermal energy. In the problem overview, there are variables that had given values, and there are variables in which the values need to be calculated by each team. In the modeling approach, we chose 50% propylene glycol as our working fluid. This was because it prevents against corrosion, has a low toxicity, and protects the tubes against bursting and freezing. The material that we chose was aluminum 661 T6. Although it has a slightly lower thermal conductivity rate than copper, it works better with potable water, and the T6 alloy is actually tougher and stronger than copper. The cost function was directly proportional to beta, and using HEEDS, the cost function allowed us to maximize beta and minimize the NTU.
In HEEDS, we used 4 variables to optimize our heat exchanger. These included the tube length, the number of baffles, the velocity of the fluid, and the velocity of the water. There are also a numerous amount of responses associated with these variables, and these responses needed to be constrained in order to remove any infeasible designs. The 2 main constraints that we used were the pressure drop and baffle spacing. We determined the minimum pressure drop needed was around 10 kPa just to ensure we had proper fluid flow, and a minimum baffle spacing of 1/5 the total length. In HEEDS, we maximized the cost, which is essentially just a weight factor times beta, and minimized NTU. Our optimal solution came out to be as shown. It was 1/4 inch tube, schedule 40, had 206 tubes, 4 baffles, and was 2 feet in length. The minimum, or the baffle spacing, was 0.12 meters, which came out to be 1/5 the length, and had a beta of 124.19 and an NTU of 0.03. Along with the design, we do make a few recommendations. It's important to keep the velocity between 1.4 and 2 meters per second, as a high velocity will increase corrosion and promote erosion. A low velocity is going to lead to stagnation or will in turn lead to corrosion as well. And it's important that we utilize some kind of filter or screen that's going to eliminate dirt, sand, other abrasive materials like that from entering the heat exchanger, and it's just going to improve the longevity and lifespan of the heat exchanger.
We decided that due to the number of tubes that we had, we actually needed to clean the heat exchanger through chemical cleaning. This was to prevent buildups and to ensure that sanitary needs were met. And for our company, we chose Exergy Company. They specialize in small, compact, high-performance heat exchangers, which perform well in high temperatures, high pressures, and highly corrosive environments. They also pride themselves on safety and sanitation. Questions?